Okay, so good evening. Again, welcome to today's set colloquium. The topic of which is why strong interactions are important to study. I'm sure some of you must be wondering how phenomenologists like Professor Indumathi is giving an asset colloquium, which is largely an engineering forum where we discuss matters which are connected with detectors, electronics, software, and so on. And probably she will say her initial days at TFR, and just in case some of you are don't know, Indu actually started her PhD in TIFR and working along with Professor P.K. Baba and Amit Roy and so on experiments. In fact, her paper in 1986, it actually reads as Search for Light Neutral Particle in the Decay of the 3.68 MeV state in carbon-13. And in fact, later on, last more than 20 years, she has been with the India-based Neutrino Observatory, in fact, from the very inception, maybe even before the inception, I must say, because the whole thing happened at a web conference which was held in, I think, IMSC, and she was part of that. And I know has been a large engineering intensive experiment, and she has been part of all the bolts and nuts, besides even going traveling all over the country to along with Professor Murthy and others to find a suitable place for INO, etc. So I wanted to kind of plead that she's very much an experimentalist, and therefore she deserves to give a if that is the right word. But okay, just coming apart from all jokes apart, she just to formally introduce today's speaker, she did her MSc from Madras Christian College and PhD. So later on, she shifted. I said that she joined TIFR, but after a couple of years, she shifted to IMSc to work with Professor M.E.N. Murthy, where she did her PhD. She worked on the spin structure of the proton. Now, after that, the postdoctoral appointments were at PRL, Physical Research Lab, and also University of Dortmund in Germany. And then she also, with a brief stay at IISc before she was appointed as faculty at Harichandra Research Institute, HRI, Allahabad. And then she came back, she returned back, let me say, to IMSc in 1998. Of course, her prime area, as I mentioned already, is in high energy physics, phenomenology, and her interests include work on atmospheric and solar neutrinos, which have been her main field of work for many decades now. And as I already mentioned, she has been a very active member of the INO project. She has been also the front face of INO, I must say, because she was the the outreach efforts she was actually running herself. She is the coordinator of INO outreach programs. Okay, so with those, I think a few words of introduction about today's speaker. I invite Professor Indumathi to take over and deliver this colloquium on why strong interactions are important to study. Over to Indu.
Yeah. Thanks, Satya. Thanks for the introduction. I want to start with a few apologies. The first apology is that I'm myself not satisfied with the way I put this talk together. So you will find out in the course of time. And the second is that I have actually just more or less highlighted the kind of work that I have been involved in. So this is certainly not an overview in any sense. And the third and final apology is that it is extremely elementary. I made it as introductory as possible because I was expecting a very mixed audience. So if there are any experts in the field, I suggest that they leave right now. So I also want to apologize because I have skipped, and you will see any mention of neutrinos in this talk. So with all those apologies, now let me start. So I've started, since, as I said, I didn't know who the YouTube audience was. I have this always mandatory set of very, very introductory slides for people who are not in the field or maybe who are just doing a bachelor's. So let me start out with okay, forget the overview, but let me start out with what we base our theories on. So I'm, as Satya pointed out, I'm a theorist, and what is called a phenomenologist. So how we understood more and more about what matter is made up of. So matter, as we know, is made up of particles. We started out with understanding of atoms, which in fact Einstein showed through Brownian motion that atoms exist, whereas light is made up of waves. So it has a wave nature. And we have written by, I think, even high school or certainly in college, Maxwell's equations of electrodynamics, which shows that light travels like a wave with the velocity, which is the velocity of light. However, we also learned that light also behaves like a particle, and in this avatar, it is called a photon. And this photon is a light quantum, and you can think of it as being a particle, so that light shows both particle and wave-like nature. And in fact, this was used by Einstein, sorry for the spelling mistake, to explain the photoelectric effect, for which he got the Nobel Prize. So the way the light quantum works is that we know the frequency of light is, say, frequency nu. Then the energy associated with the light photon, which is the particle, is h times nu, where h is that Planck's constant. So this is the relationship that quantum mechanics proposed between light as a particle and light as a wave, and therefore light is supposed to have a dual nature. Now what happens is that de Broglie comes around and says that electrons also have a dual nature, a little bit different, because electrons show their wave nature when they have a non-zero momentum. But in essence, both electrons and photons therefore have a dual nature and show both particle-like and light-like and wave-like behavior. And based on this and the uncertainty principle of Heisenberg, quantum mechanics was formulated. And in 1928, Dirac actually extended the notion of quantum mechanics to be consistent with the special theory of relativity. Now, to be consistent with special theory of relativity, two factors were introduced by Dirac. One is the notion of spin, which I think all of you have learned in chemistry, that electrons have a spin of half h cross, and the notion of antiparticle, and I will come to that in a little while. So for example, you have particle proton with positive charge, antiparticle antiproton with negative charge, electron positron, pairs which have the same mass but opposite charge. In fact, all charges, not just electric charges, but any other charge that they might have will become conjugated. So many theorists felt that there must be some symmetry, surely, which exists, which allows for such similarity to have two kinds of particles with the same mass but opposite charges. And this was formulated in a very formal way. It's called quantum field theory, which is just basically take quantum mechanics, take some principle of symmetry which allows this certain equivalence to occur, and special consistency with special theory of relativity, and put together that forms of quantum field theory. So now let me show you an example, because instead of going abstract, let us look at various kinds of quantum field theories. So quantum field theories describe the properties and interaction of particles. So let us take, for example, simple electron and proton. So what happens, as an example, electron and proton can bind together to form a hydrogen atom through electromagnetic interactions. And every field theory has what is called a mediator. And in this case, our familiar photon becomes the mediator of the electromagnetic interaction and the physical consequences that atoms are formed. So we can understand all the interactions or the fundamental interactions that we know through this paradigm really of particle physics. For example, all particles, doesn't matter, I'll tell you what these are later, experience something called weak interactions, which you would have learned as radioactivity, for example. And the mediator for those weak interactions are three particles actually, W plus, W minus, and the Z boson. Similarly, strong interactions are mediated by particles called gluons, and the physical consequence is that the nucleons, the protons and neutrons, are bound together inside an atomic nucleus. And of course, all matter experiences gravity, and that is through this mediator called the graviton, and the physical consequence is the formation of the universe. So this is the basic idea that we have, that you must be able to understand interaction between particles as being mediated by some particle, and all these particles are actually, the mediators are all spin 1 particles. They're all bosons, except the graviton, which is also a boson, but a spin 2 particle. So based on all these, standard model of particle physics has been set up. There are 4 fundamental forces, which I just talked to you about. Gravity, which we know about, electromagnetic, strong and weak. So by negation, leptons are defined as those objects which do not experience strong forces, which are not sitting inside the nucleus. And baryons are defined as those objects which do sit inside the nucleus, which do experience strong interactions. So, for example, here, I'm leaving out gravity from now on. So let's take the three remaining interactions. So proton has a charge, experiences electromagnetic interaction, sits inside the nucleus, it experiences strong interactions. And you can see that everything will experience weak interactions, right? However, the electron does not experience strong interactions because it doesn't sit inside the nucleus. And of course, the neutrino experiences only weak interactions. So here are these particles I have introduced. And formally, we say that they come, these leptons, so these objects, the charged leptons and the neutral leptons, are actually can be put into a kind of vector basis like this. They're called flavors or types or generations. And the familiar electron comes with its neutrino, and heavier copies of these called mu and tau come with their neutrinos. And we don't understand why there are three flavors of these leptons, but you will find that there are also three flavors of the quarks. So what are these quarks? It turns out that baryons are not fundamental particles. They are made up of different quarks. So quarks are actually things which out of which baryons are made. So the proton is not an elementary, that means it's a composite particle. It's not a point-like particle unlike the electron. It's made up of quarks like U and D, and it's the quarks which are elementary like the electrons and muons. So for example, the familiar proton and neutron are made up of two U's and a D or two D's and a U quark. And you can see that because the proton has +1 charge, the U quark has 2/3 charge of the proton each, and the D quark has -1/3, so that 2/3 plus 2/3 minus 1/3 is 1, and the neutron comes out to be neutral. And why are they three quarks? And this is the new idea that happens when you talk about the theory of strong interactions. It's the notion of another charge. It's called the color charge. So when people talk about color, it is an analogy with light, because as you can see from my table, there are three colors, red, green, and blue, but it is really a charge. It's a generalized charge like you have electric charge. And all quarks come colored. There are no colorless quarks, but by putting red, green, and blue together, the overall baryon that is produced, or the hadron that is produced, is colorless. And therefore, we use the analogy with light that red, green, blue primary colors compose together to form white light. So this is the origin of the word color. And just like we had three flavors of leptons, you also have three generations of quarks. And U and D, as you can see, come in our ordinary proton, neutron, and in fact the pion also. But the others are more exotic, and they form more exotic baryons, all of which have been seen to exist. So both quarks and leptons are spin half particles. So now that we have learned so much about quantum field theory, let us look at antiparticles. What Dirac posited, that there are antiparticles like proton and antiproton with the same mass and opposite charge. But the way to understand really what an antiparticle is to look at Einstein's mass energy equivalence. So what Einstein's mass energy equivalence says is shown in this diagram. You can see that a positron and an electron come together and they annihilate into a photon. This is not a complete diagram. I don't want to go into the technicalities of it, but basically the mass energy of the electron-positron can be converted completely into light energy. So production of photons actually occurs, and therefore the notion of mass energy equivalence is that the mass can be completely converted into energy when the particle and antiparticle annihilate each other. This diagram also serves as a very nice basis to understand what we mean by coupling or interaction between two particles. What do you mean by coupling or interaction between two particles? Let us look at the scattering of two electrons. Two electrons must actually repel each other. Why do two electrons, or not why? Why is not a question to be asked in physics. It's really how. How do two electrons repel each other? By exchanging this photon, which is the mediator of electromagnetic interactions, which kind of carries the information from this electron to this electron, as a consequence of which they repel each other. And if you put a positive charged object on the other side, then the information would have been one of attraction rather than repulsion. But this diagram tells us a very important quantity, that at every time there is a vertex or an interaction between the mediator and the charged particle, the strength of this interaction is proportional to the charge of the particle. And therefore, if there are two vertices over here, there are two quantities E over here, and therefore this object, the rate of this process is proportional to E squared, the whole squared, because this is the probability amplitude whole squared, and this E squared is related to what is called alpha, which is the fine structure constant. So this electron couples to the photon proportional to its charge. Similarly, every particle couples to its mediator proportional to the charge of that interaction. So this is really, again, the paradigm of particle physics. So forces are created or generated by exchanging the force carriers, and the strength of this interaction is proportional to the charges that are involved. That is, so how do we understand these charges? One way to understand these charges is to look at Heisenberg's uncertainty principle. Therefore, if you have, for example, look at the previous diagram, this electron has emitted a photon, and sometime later this electron has absorbed this photon. This is how we understand this diagram. The amount of time delta t for which this photon is emitted and then absorbed is related to its energy. So if you want to emit a higher and higher energy photon, you must you have only lesser and lesser time in which to do it because of Heisenberg uncertainty principle. You can invert the delta E to get the width or the lifetime of the particle, and that will be, of course, related to the coupling constant, or the square of alpha, which is the electromagnetic coupling constant in this interaction. So you can do the same thing for all kinds of interactions, electromagnetic, strong, weak, and you will find the following things. You will find that the decay rate, which is the inverse, which is the lifetime, actually. This is not decay rate, sorry, this is wrong. One is the inverse of the other. Decay rate is the inverse lifetime. Here I'm writing down the lifetime. So for strong interactions is 10 to the minus 23 seconds, for electromagnetic 10 to the minus 16, and much larger for weak interactions. So strong interactions are very fast, electromagnetic interactions slower, weak interactions take long time. And if you invert it, then that means that the strength of the interactions are in the ratio of 1:100:1:100,000. That's why weak interactions are called weak. So now we have the entire setup. We have understood, because of the way we have set up the interactions, that the vertices couple with the strength of that interaction. Weak interactions are weak because the coupling constants are small, and strong interactions are strong because the associated coupling constant is large. Now, what is the gauge principle? Let us go back to electrodynamics. Electrodynamics, we have already seen the first diagram. Now you can see I've just rotated this diagram around in many ways. Okay, but whatever I do, there is no diagram in which the photon interacts with itself. There is no self-interaction of a photon. That is because photon is the mediator of electromagnetic interactions. It couples to charged particles. Since the photon has no charge, it cannot couple to itself. This is in complete contrast to quarks, strong interactions, or in fact, even for weak interactions, because both weak and strong interactions show self-coupling. So here I show these diagrams. So you remember there were 6 flavors of quarks: up, down, U, D, CS, bottom and top. Each came in 3 colors, red, green, and blue. The mediators of these interactions are gluons. There are 8 colored gluons, which are massless. And this spring that you see denotes a gluon, and the straight line denotes either a quark or an antiquark. So not only do you have a diagram which looks like a photon goes to a quark-antiquark pair, but the gluon can actually split into 2 gluons or 4 gluons. So it has so much self-interaction. This is also partly why strong interactions are strong. It also makes life hard to calculate, because these interactions are allow for many more contributions, and therefore the cross sections or the rates of interactions are much harder to calculate for strong interactions than for weak interactions. So let us take a simple example. We said that quarks have color. How do we know quarks have color? We had this diagram, which I said was electron-positron going to photon, and then that photon can again produce an electron-positron, or it can produce a muon-antimuon. It can produce any pair, including it can produce a QQ bar pair. Since the quark has fractional charge compared to the muon, the ratio of these rates, so sigma is related to the rate of the interaction, the number of events that you'll see in the detector, this ratio will be proportional to the charge square over here, because you're going to square this diagram. So if you look at the charge square, roughly, if you have only UDS light quarks, or if you add the 4th flavor or the 5th flavor or the 6th flavor, sorry, it's gone out of the page, you can see that the number of the ratio will be of the order of 1, 2/3, 10 by 9, 11 by 9. But if you actually look at the experiment, what you see is that the ratio is actually 3 times that. So instead of being 1, it's actually much, much larger. And that's because you not only have this diagram over here, but you have one such diagram for a red quark anti-quark pair, one such for a blue quark anti-quark pair, one such for a green quark anti-quark pair. So really what you should have had is a factor over here, which is proportional to the quark color. You should have had a factor 3 times EQ squared. And this is the evidence for quark color. So this is what we now know about strong interactions. We have understood that this is the way in which quarks interact with each other through gluons, and they cause the protons to sit inside the nucleus and be confined in a very, very small space, because the nucleus is 100,000 times smaller than the atom itself. And that very tightly bound structure is because of the strength of the strong interactions. So here is a slide now where I have kind of done a small jump to a little bit more technical point, but I hope that you will be able to understand it. So what I have said is that I've started out by saying that just like alpha, which was the fine structure constant, was the coupling constant for QED, alpha strong, which I denote as alpha S over here, is the coupling constant for strong interactions. Okay. But now what happens is that it turns out, because these coupling, the strong interaction is very strong, this alpha S is very large. We expect it to be much stronger than electromagnetism, which was 1 by 137, right? That's the fine structure constant. So you can see that it's of the order of 0.4, 0.5 at low energies. So Q denotes some energy scale. However, you can see that as the energy scale increases, this alpha is practically going to zero. You can see that already from in 2 orders of magnitude, it has gone from 0.4 to 0.1. And in fact, we do believe in this theory that there is something called asymptotic freedom, and that literally if you supply infinite energy to the quarks and gluons, then the coupling constant actually will go to zero. So this is called asymptotic. They are asymptotically free when they are at very, very high energies, or as Heisenberg says, at very, very short distances. That is the meaning of Heisenberg's uncertainty relation. So if you probe deeper and deeper into the proton, or deeper and deeper into any composite structure which is made up of quarks and gluons, then you will find these quarks and gluons are asymptotically free. But the moment you try to pull them apart, and that pull them apart means that you're trying to bring them apart by separating them by large distances, then they start being very tightly coupled to each other, and that's why you cannot pry them apart. And because you cannot pry them apart, the quarks get confined within the nucleons, the protons or the neutrons. And so the same property of the strong coupling constant, that is, this is called the running coupling constant, or the scaling behavior as a function of the energy scale, causes both the quarks to be bound inside the proton as well as to be asymptotically free when you probe them at very high energy. So this is one technical statement that I am making, but this actually will influence a lot of the things that we are going to calculate. So this is a very important concept to understand. Okay, so the question now is, how do you probe the partons inside the proton? So we have maintained that there are quarks. We found that you could explain that there were 3 colors of quarks by looking at certain processes. And we also said that the quarks comprise quarks coming together as UUD quark make up the proton, and 2D and 1U quark make up the neutron. However, we just showed that the coupling is very, very strong. Because the coupling is very, very strong, the proton turns out to be just not 3 UUD quarks, but lots and lots of quarks and gluons are there inside the proton. So how do we understand this? We understand this through a process which is called deep inelastic scattering. This is deep inelastic scattering, and the leftmost diagram tells you what is deep inelastic scattering diagrammatically. So L is a lepton. Let's say electron comes in and scatters off a proton. So this red object is a proton, just to show that it's not a point particle, right? Now what happens? If the energy is small, then the electron simply sees the proton as a point particle. For example, if you remember Rutherford scattering, even the alpha particle sees only the nucleus in the middle of the gold atoms, right? That's it, nothing more than that. However, if you have higher and higher energy, then we just saw that you can probe shorter and shorter distances because of Heisenberg uncertainty principle. And therefore, these electrons or these leptons will start seeing the quarks inside the hadron, inside this proton. So it can actually interact with one such quark. And as it has higher and higher energy, the coupling constant alpha s is small. These quarks are quasi-free. And so they don't talk to the remaining quarks and gluons. And I can have a single quark scattering of this electron and coming out. So this is called deep elastic scattering. And because one quark is lost, the whole hadron breaks up and produces lots and lots of final state particles, which are collectively called X. So this is the whole idea. So how do you understand this? We say that there are quarks inside the proton. The way in which these quarks are distributed inside the proton and carry its quantum numbers is very characteristic of those quarks. The way this is written down technically is to say the probability of finding a quark inside the proton is called the quark distribution function. Similarly, the probability of finding a gluon inside the proton is called the gluon distribution function or the gluon density distribution. And what is this fraction X? The fraction X is the fraction of momentum that the quark carries with respect to the, so if the proton is carrying say 1 GeV, 10, let's say 100 GeV of energy, and the quark carries 90 GeV of energy, then X is 90 by 100, which is 0.9. So this fraction is the momentum fraction carried by the quark, but we already said that quarks are confined. I'll never be able to see this final state quark. I will show you later that this quark also gets converted into hadrons, like protons and pions and things like that. So how in the world will we be able to measure this quantity X? I will not show you any equations, but it turns out that this fraction X is actually related to kinematically measurable quantities. Like, for example, the scattering angle of the final state electron or its energy, and therefore it is a fully measurable quantity. So by measuring certain kinematic properties, I can actually tell you that the momentum fraction of the quark which was struck by this electron is so much %. Okay, that is an amazing thing. However, what makes life complicated is the fact that these are all experiencing strong interactions. So how do you know that this quark that is interacting was actually just sitting inside the proton? It could have just been produced in the second diagram when a gluon produces a quark-anti-quark pair, or it could have been produced by another higher momentum quark emitting a gluon, and so on, right? So there are many ways in which this quark could have been produced. Similarly, the probability of finding a gluon inside the proton, this gluon could have come from some higher momentum quark, or because there are self-interactions from a higher momentum gluon. So life becomes much more complicated. But however, these what are called splitting functions, that is how a quark or a gluon splits to form lower momenta quarks and gluons, can actually be calculated in the theory. Since this vertex is a gluon vertex, and we know that it is proportional to the charge or the color charge, we know that these corrections will be of the order of alpha s. They are not small because alpha s is not small. That is the meaning of strong interactions. However, there are two consequences. One is that it's important because alpha s is large to include higher order contributions. However, because there are higher order contributions, there is what is called a scale dependence. The alpha s itself, as we saw, and also the properties of these quarks and gluons, the distribution functions start to depend on both x and q squared. So this is called scale dependence of the distribution functions. So it turns out that because at low values of q squared is this energy scale, the momentum which is flowing into the hadron vertex, the square of the momentum flowing into this proton vertex. When q squared is small, we cannot calculate anything because it's a completely non-perturbative theory because alpha s is large. But as q squared becomes larger and larger, these alpha s corrections are actually completely perturbative, and we can calculate them order by order. So I've borrowed the slide, may not be very clear. All you need to realize is that I can calculate the corrections order alpha s squared, order alpha s cubed, and so on. And I think maybe I don't want to go over the rest of it. So I can calculate these corrections order by order in the perturbation theory. However, I have to start somewhere. I have to suppose I start at some low q squared. I can calculate the higher q squared corrections because they are perturbative, but at a low enough value, I must actually look to experiment for the answer. So if I have the experimental result, then by using the theory of QCD in its perturbative regime, I can find out the results at higher momentum square. I have a small technical point to make here, which I will try to make in a non-technical way. Here we talked about deep inelastic scattering of electrons on protons. Electrons are extremely well known. We was just one moment, please. Come in. I'm giving a talk. Can I meet you later? Yeah, fine. So sorry about that. Suppose I don't have, so electron was very clean. The proton is what was unknown, and we were trying to probe its structure by understanding how the quarks and gluons carry its quantum numbers, how they carry its momentum, how they carry its spin, etc. Suppose I have two quarks, two hadrons, HA and HB, which are colliding. Then both are red dots, right? Both the vertices are completely unknown. So you have really a lot of difficulty in understanding this expression. However, there is something called factorization, which helps us. So what happens in factorization is that I can separate out the probability of producing a quark or a quark bar from these two expressions. And I can separate out the probability of the QQ bar interacting to form some final state, and so on. So each part I can separately calculate, and then I can some technically multiply. It's called convolute these results and get the final answer. So this factorization helps us because then every vertex is very similar to what we already saw in the deep elastic scattering. So there's some adjustments to be made. So some definitions will have to be done. But once you do those definitions, then of course, these are universal parton distributions. So what does that mean? Whatever process I have, whether I have PP collisions, EP collisions, PP bar collisions, the moment I know the parton distribution functions, I can apply it at every one of these vertices, and they are universal. So this is a very, very important point to keep in mind. Otherwise, if they're all very different, then there is no point in actually trying to understand how the quarks and gluons are distributed inside a proton. Okay, so here is an example. Because there are many. So as I said, this is completely theoretically done. This is very important to understand. You have to start out with some input values. So why do we need an input value? Because I said that I do not know the answer at some low energy scale. I have to take it from experiment. But once I take the results at some low energy scale from experiment, then QCD tells me how to go to higher and higher Q squared or higher energy scales. So here I have some set of data was input. And in fact, that's actually a really big complication to try to understand the consistency of the data that was input. I will talk about it a little later. So this is one of the latest. So I showed you just one splitting function, right? That is what is called a higher order or next to leading order. This is next to leading order PDF. So many higher order corrections have been made in computing these quantities, and some input has been taken from experiment. So on the left hand side, what has been done is that they have fitted it to some low energy where Q squared is 10 GeV squared. And then using, as I said, the theory of QCD, they have predicted the values starting from these values for 10 to the power of 4 GeV squared. And what I want you to see is this. If you look at this is for the proton. Proton consists of 2 U quarks and 1 D quark. So the main U and 2 U's and 1 D are called valence quarks. You can see U valence and D valence. U valence being about twice of the D valence because there are 2 U quarks. So that it has twice the probability of being found. Also, you can see that it peaks around 1/3. So in the limit, when it was not a strong interaction, if there were just 3 quarks, each of the quarks would carry 1/3 of the momentum fraction, which is what is plotted on the x-axis. And now it gets spread out because of the big sea of quark-anti-quark pairs that are caused because of these splittings. Gluon goes into QQ bar pair, Q radiates a gluon, which then goes into a QQ bar pair, and so on. These are called the C distributions. And therefore, you also have S, which is strangeness, charm, U bar, D bar, gluon, everything. All distributions are non-zero inside the proton. And the second thing to realize is that because of the way in which the theory works, the gluon distribution function, even if you start out with a small value at low Q squared, becomes really huge, because you can see this is G by 10, which is being plotted, and it just completely dominates the scene at small momentum fraction, because you can understand that physically, right? As you go to smaller and smaller momenta, those quarks and gluons are obtained by higher and higher splittings, and therefore there are more and more of them. And it also turns out that gluons carry about half the momentum of the proton, with the remaining half being in quarks. So this is how we understand really what is going on inside the proton, how you can understand the properties of the proton in terms of the quarks, and so on. So let us see how one application of this. Why I asked, why is this important? Why are we interested in knowing this, right? So the statements are the following. Just 3 statements. Don't worry about what these experiments are. Okay. There was a Hera collider in prehistory when I was doing my PhD. It's an electron-proton collider. Nicely did deep inelastic scattering, and the parton distribution functions, which are called PDFs, were measured from Hera. But it was at low energy. The energy was electrons at about 28 GeV, protons at about 1000 GeV, and the root S, or the center of mass energy, is about 300 GeV. Now you take that and then you use your theory and extend it to the Tevatron collider, which is a PP bar machine, which is at a much, much higher center of mass energy of nearly 2000 GeV. Here, this is almost 2000 GeV. Similarly, you take those same parton distribution functions and extend it. I think all of you should know LHC, so I don't have to describe what is LHC. It's a PP machine, and now running 7, 13, 14 TeV. So 14,000 GeV. So the question is, how correct are you in doing this? How much error do you actually generate in extrapolating your PDFs, which you measured at much lower energies? Is your theory correct? So these are all the questions that we have to ask. And here, I'm sorry, these are small. I hope you can see them. The leftmost graph is actually a kinematic region of X on the X-axis and Q square on the Y-axis. And the green color, you can see, they're practically triangles, right? The green color is what has been physically measured by the Hera experiment. And those values are being used for the blue big triangle, which is the LHC experiment. So you can see how much of, because these are orders, you can see that from 10 to the minus 1, and the top of the green triangle is at 10 to the 8, right, GeV squared. So you are going like 6, 7, 8 orders of magnitude in Q squared. And similarly, you're going another 2 orders of magnitude down in X. So you're going to get huge uncertainty. So for example, if you look at the rate for gluon-gluon fusing into the Higgs boson, it's a very big thing which happened about 10 years ago when the Higgs boson was found. But if you look at the little inset, it tells you that there's a plus or minus 5% error coming from the green, the blue, and the red, which are 3 different sets of accepted parton distribution functions, which have the same quality of fit for Hera, but actually differ when you come to the energy scales relevant for the Higgs. And the right-hand side again shows the same thing, but in a little different way. It doesn't matter. So you can see that these two, of course, this was, you can see that the inset is important because these were predicted or calculated before the Higgs was found. As you can see, this is a 2003 paper. Higgs was found in 2012, and therefore you can see that it was a very, very hard job to make sure that you had your cross sections right and that you were actually seeing some new physics or some different physics. Because if you don't understand your standard physics, then how are you actually going to be able to look at new physics and predict new things or look for physics beyond the standard model? Okay. So that was one example of deep inelastic scattering. Let me go on to another process which also involves strong interactions, which is the reverse process of deep inelastic scattering. In deep inelastic scattering, we probed how the quarks make up the proton. So we had electrons colliding on a proton, and we asked what was the proton structure. Now what we do is that we are actually colliding electrons on positrons, so we don't have any hadrons, any strong interacting particles in the initial state, but we are producing hadrons in the final state. So this is what is called a semi-inclusive process. And how does the hadron get produced? Let us say we already saw E plus E minus can produce a QQ bar. And one of the quarks, and you can see on the right-hand side figure, one of the quarks, because the vertex, the strong interaction vertex is strong, it can emit the soft gluon, which then goes into a QQ bar pair. And this QQ bar, for example, this is a quark-anti-quark pair, is what forms a pion, a meson, or any of the vector mesons like rho, omega, or strange meson like K, K star, and things like that. So this is called hadroproduction. And lot of times in the experiments in LHC, in Tevatron, people are looking at final state mesons and trying to, especially for flavor physics, and they have to go back and try to see what is the physics that produce these hadrons. So this is also a very important interaction. And essentially, it's an inverse process to parton distribution functions. And the uncertainty comes in the final state. So instead of X, which was the fraction of momentum of the proton that the quark carried, Z is the other way around. If the quark came out with 10 GeV and the hadron is 9 GeV, then Z is the fraction of momentum of the quark that the hadron carries. So it's simply the other way around. So there's a huge relationship. In fact, this is a time-like process, the other is a space-like process. So you can actually relate the quantities which are involved in the two cases. And just like we had initial state hadron, it was called a parton distribution function. Here it is called a fragmentation function because it shows how the quark fragments to produce hadrons. And again, there is a scale dependence. Again, these are perturbatively calculable, and you can do the whole story all over again. And then what do you get? So here is a study. So these are very, very difficult experiments to see. So there's very little data, as you can see. I didn't show you actually DIS data. There are some 2,000 data points. Here, there is only a handful. So on the top two, you can see in the top two graphs, I've shown vector meson production rho, omega, k star, phi, and some theory which is the straight line fits to this data. So these are all E plus E minus, which I just showed you, which are very clean initial states, and therefore I can very cleanly find the fragmentation function for whatever h, that is h is equal to rho or omega or k star or phi. Now I take this result and then I apply it to PP collisions. This is the RIC data, which has PP collisions where omega or phi are produced. And this is at 200 GeV energy, so it's much higher energy than the LEP experiment. But you can see that from the prediction from here to here is still reasonable. So if I can fit it to one set and then I predict it to the other set, I do have a reasonable fit. But, and of course, before I go to the but, let me make another statement. One of the very important questions in QCD is something called saturation. What does saturation mean? If you go and look in the previous, this graph over here, you look at this. This tells you that because of strong interactions, gluons can split to two gluons, right? So this can produce an infinitely many gluons inside the proton, but at some time this process must stop because you'll have so many gluons, the density of gluons becomes so high inside the nucleus that the reverse process will happen. The two gluons will actually fuse back into one gluon, and therefore you should see a saturation in the increase of these distributions. And this is actually seen, as you can see over here. If you look at this region over here, you can see the turnover, which did not happen for the deep elastic case. There, the gluon density was going up and up and up, but you can see here, they're actually turning around. But searching for the saturation effects is one of the very important open problems in QCD, perturbative QCD today. Anyway, coming back to our main story, here we had these mesons from E plus E minus scattering. You fitted them, and then you fitted them to PP data at low energy at 200 GeV, it looked fine. But you see what happens now, I fit it to the 7 TeV LHC data. So this is now the ALICE data at 7 TeV. So from 200 GeV, I've gone to 7,000 GeV. And you can see the blue is now that same fit, that same code, same theoretical fit. And if you look in the bottom, you can see that although this is over some 6 orders of magnitude, it looks very impressive. But if you look at the details, you can see that the theory starts to deviate from the data at larger PT. So of course, this is limited by sparse data, but the main problem is that the data sets have very, very small overlapping kinematic range. So it tells you the danger of having a fit or an understanding of the physics at some energy or X region and trying to extrapolate it to some other region. And therefore, it again becomes important to understand these distributions much, much better. Okay. So here is a futuristic, in fact, the only, I think, future collider that has been approved in the US. It is a replacement for the FRIB experiment. It will be at RIC. It is called the EIC, or the Electron Ion Collider. It is supposed to come online in 2032. I want to make 2 points in this slide, which has been borrowed from Abhay Deshpande's talk. He's leading this collaboration. So the two things are the following. One, I did not talk about nucleon spin. I only asked how was the momentum of the proton shared among its constituent quarks and gluons. You can ask the same question for spin. We know that the proton is a spin half object. So its spin has to be shared between the quarks and the gluons because the gluon is a spin one object. However, in this equation, there is also orbital angular momentum of both the quarks and the gluons. This is a much more complicated process. There are very interesting things. Some little results have come from RIC. You can see in the graph over here that this is the RIC data, and the theoretical predictions that have been made, especially for low X, for something which is essentially a distribution function for the spin-dependent case, can be extrapolated to all these dotted lines. So you can see that there is absolutely no information below x is 10 to the power of minus 3. But you need to use many of these for your other colliders and the more futuristic higher energy colliders. So it becomes important to measure them. So this is one thing I wanted to say about the spin. And of course, the EIC itself will measure things to much better precision. So there are going to be more experiments which will better understand these Paton distribution functions. Now, I want to make a small example of W boson mass. You might have heard that recently in April, the CDF2 collaboration measured a W boson mass, which was 7 sigma away from the gray line, which is the standard model prediction. And the other experiments, including the CDF1 data, were more or less consistent to within 1 sigma with the standard model prediction. And you can see that the error bar is really small. The error bar is plus or minus 9, whereas you can see that in the case of the Atlas experiment, you can see that the error bar was much, much larger. So, and that is the next best result actually, where it has the next smallest error bars. So what is it that has gone into this? That is what we must ask. So I'm sorry, I hope you can actually see this. You can see that the largest error, the uncertainty over here, which is 3.9, is actually coming from the Paton distribution function. So this 9 that you can see, the error bar of 9 that you see over here, which is 9.4 actually in total, almost half of it is coming from the uncertainty in the Paton distribution function. The same thing you can see, this is CDF2 data, the older Atlas data. You can see that it had 19, you remember, it had an error of 19. And you can see that depending on whether it's W plus or W minus, because it's a different experiment, you can see that out of 19, 13 or 14 are actually coming from the PDF uncertainties. So substantial fraction of the error bar actually arises from the uncertainty in the Paton distribution functions. So if you want to know the W mass, and if you want to see whether there is new physics which is hiding in the W mass measurement, then you must know again your standard model measurements very well. You must know your QCD very well. You must know your Paton distributions very well. So the other thing, little more subtle point, is the input versus output problem. So I had already mentioned this NNN PDF 3.1 fit, which is used to fit the data, the Paton distribution functions from HERA and many other experiments, and then evolve it down up to the Tevatron or to the LHC result. There are many, many tables, but this is just a sample table of the experimental inputs that they have used. For example, from this experiment, they have used this data. This is the reference, and this is the kinematic range in the PT or the mass or the Q squared or whatever. And you can see over here, I have highlighted that there is a W electron or W muon asymmetry, which comes because this is a Tevatron PP bar experiment. And therefore, the W being UD bar or U bar D, the U will come preferably from the P and the U bar preferably from the P bar. So there is a direction asymmetry in this production of the W, which then decays to either electron or muon and neutrino. But you see that they have taken the data and they have used the Q squared to be the mass of the MW squared. What does this mean? I have used a certain Paton distribution fit, which is based on some data, but that data is based on data which has come from the mass of the MW from earlier CDF data. And I'm using this now to fit the new CDF mass, right? So the question is that, have you got your inputs and outputs right? Are you consistent between the two? This is of course going to be a small effect because the Q square dependence is logarithmic, but still once life becomes so complicated and you have so many inputs and outputs, it becomes very important to make sure that you're not getting a result because of what you put in, but it's a genuine result. So these are the questions that become exceedingly important when you start combining older and older results, and somebody has to really keep track of whether they're doing it the right way. And of course, a lot of reanalysis of this data is going on, and I'm sure that people will comment on this. Okay, so I want to spend the next 5 minutes on something which I don't want to go into very deeply, but just to tell you that, okay, all these problems are happening in QCD, and because QCD is dirty, protons are not elementary. So maybe just forget QCD. Just always have clean things like electrons, positrons, photons. But actually, it turns out that it's a problem because, after all, what is a photon? A photon can also produce a QQ bar pair, and it's very likely to do so because the strong interactions are strong, and therefore, once a QQ bar pair is produced, it will produce gluons, and the gluons will produce further QQ bar pairs, and this is what is called the resolved photon. So there are two steps here. One is that I have electron proton experiment. The photon is what comes in. This is my standard deep inelastic scattering, produces something. I wanted to look at heavy quarks. That's why CC bar is my final state. However, it's possible that this photon itself, because inside it, it can produce, it can radiate quark anti-quark pairs, which can produce gluons. And so I can actually find the parton distribution functions of photons themselves. So I can have once resolved, twice resolved photon-photon colliders, and there is a lot of physics in that. For example, charmonium states in such highly resolved photon processes have been very greatly studied. I just want to show you a result. So this is some calculation that was done. So you can see that this is the once resolved and twice resolved photon. Doesn't matter what they are. The contributions are quite large. So you can see that if you don't take a certain contribution in this calculation, then you will not agree with the data. This is the Delphi data over here, and this is some fit to that data. So you can see that even some clean system, which you thought was very clean, electrons and photons, actually do also involve your quarks and gluons because of the very large strength of the alpha is this thing. So here is my blank slide on neutrino physics. There is a huge amount of input of QCD into neutrino physics because every neutrino interacts with a nucleus. If you look at any neutrino experiment, whether it is iron that ICAL wants to do, or whether it is water, or not the electron, but the interaction with the proton, with the oxygen, with your scintillator, with anything that you have, the neutrinos interact with nuclei or nucleons, and these are at very low energies because the interesting neutrino physics has all happened due to neutrino oscillations at medium or very low energies. We are not talking about TeVs, but we're talking of GeVs or few GeV of energy. And it's really, really complicated. And a lot of new results that have come out in neutrino physics, like sterile neutrinos, looking at the mini-boon low energy data, which has a discrepancy. Everything is uncertain because of huge uncertainties in the QCD or the strong interaction cross-sections of neutrinos with these nuclei. And there are literally dozens of experiments which are coming up in the present and in the near future, which are going to measure these cross sections much more accurately. They are very difficult experiments to do, but you can see that there's a huge input of QCD into neutrino physics. So I want to end here. Actually, I want to summarize because I think that I've covered a lot of things, so I don't want to say any more. QCD is a theory of strong interactions. It posits that hadrons like protons and pions are made up of elementary particles, partons, which are quarks and gluons. And the nature of the strong interactions is responsible for quark confinement. The other side of, or the other side of the coin of quark confinement is asymptotic freedom. And because of asymptotic freedom, that is which is actually the scale dependence of alpha S of Q square. At large energy momentum transfer, it is possible to make perturbative calculations in QCD. And in particular, the scale dependencies, or so-called scaling violations, are calculable order by order in the theory. Hence, given an input set of parton distributions, it is possible to predict the distributions at a different scale, energy scale. And this is absolutely crucial, we saw, for extracting physics from machines such as Tevatron, RIC, and LHC, where inputs from older accelerators like the Hera EP accelerator have been used. And the uncertainties in these affect the extraction of not only new physics or even standard physics from present, as well as will affect the extraction from future colliders. And therefore, machines such as the proposed electron-ion collider will be very important to reduce these uncertainties, especially if you want to look for beyond the standard model physics. You want to make sure that you understood your standard model physics before you actually say conclusively that what you have seen is a signature for beyond the standard model physics. And that has proved very elusive. You know that these contributions are very small, and it becomes very important really to understand your QCD background. So I hope I have convinced you that QCD is not just something for show, but actually very important and crucial, actually, without which you could not have got any physics out of all the accelerators of today and tomorrow. Thank you very much.
Thanks very much, Hindu. That was just at the right level of what a typical asset audience would like to know from such an important topic, which in some way, as you summarized so beautifully, that without knowing well the uncertainties of QCD physics could have kind of play a major kind of role, both not only in the neutrino physics that you very
left blank
showed a blank screen, but also the accelerators and obviously the physics beyond standard model, and so nice and so beautiful. And I think most of the gist of how important this field of physics is. So I'm sure there will be, I think, some more interesting questions which will also, I think, bring up some more insights of the subjects that are dealt with. The talk is now open for questions. I request participants from the Zoom to kind of unmute yourself and ask questions. And similarly, those who are in the YouTube could also type in your question.
Do I have to raise my hand?
No, it's okay. Go ahead, please.
Okay. Yeah, it was very nice, Indumathi. Of course, initially I missed the first part of your talk, but I also take cue from what Satya has said. I think it's important that you highlight about this danger of claiming W mass is different. So, no, this is very important because people have been making a lot of hooray type of fear that, okay, we are seeing different value of W mass. So this is why precision is very much important. And as you have also said, maybe on another occasion, one can discuss about the LHC contribution for all these advancing the QCD precision. And I also like that you showed the evolution of the PDF for Q square equal to 10 GeV to Q square equal to 10 to the 4 GeV. Yeah. That's still nice.
Thank you.
That is quite nice. That particular slide is very,
I see.
The way you connected up from hierarchy to even future. Yeah, this one.
Yeah, okay.
Previous one also. I was
no, this one. Yeah.
This one.
You
yeah.
actually this one.
Yeah. No, I think. See, we should understand really. These are all really
exactly. These are at the basics, but students must need to appreciate these. Exactly.
Yeah, that's what I said. For the experts, probably it was too trivial, but
anyway, thank you.
Thanks, Kajari, for nice comments and also bringing up this important.
Satya, this is Rajiv.
Yeah, please.
Can I say?
Rajiv, please go ahead. Yeah, please.
Yeah, Indumathi, this figure is from the PDG, right?
No, this figure is wherever I have put at the bottom, it's from there. So this is from the NNPDF 3.1. EPJC 77. Yeah, it may also be in the PDG. This is the latest.
Right.
This is what CDF2 uses. But of course, they have also compared with 3 other distributions, and they said that they are consistent. See, they are all consistent in the low energy. How consistent they are at higher energy? There is, if you look at the CDF2, they have additional. They have some 80-page additional material. There is a variation. I mean, I don't understand fully what they are saying. It is not that independent that I don't know how they get their 4 MEV result, but that's what they claim. I think they have done statistical analysis. So they have these templates, and then they keep running it, and then they do a.
Yeah, the PDG group have come up with more latest version of this in 2022, this year. So PDG 2022 has another version of these figures. I don't know how much it differs from this.
Yeah. No, I only showed this because, as I said, this is what CDF2 has used.
Okay.
So, because, there are so many in the market, actually. It's your choice. Really, it's your choice.
Right.
Okay. Thanks, Rajiv, for joining the lecture and also for this question. Any other questions, please, from Zoom audience?
Just a comment, as she mentioned that there is a large Indian community participating in this EIC project.
Yes.
They are gearing up.
Yes, that is true. Yes. This is the electron-ion collider. So there is, because I did not even mention things like generalized parton distribution. I thought that will be too much. So I didn't want to say anything more, but it will measure. See, I try to make this talk as something, how will the calculations be useful for other areas, right? But on its own, our understanding of the proton structure, of its angular momentum, of its momentum, and what they call generalized Parton distributions is by itself a very nice field of research, and EIC will actually do that very well.
Okay, I could have asked you in those.
Okay, you can ask me here.
Since, since the YouTube guys are not coming in yet, let me ask you a question about this factorization. Now, how? I mean, is that something that can be relied upon 100%, or is there some uncertainties associated with this factorization?
No, it has been proven actually. So you can prove factorization. The thing is that proving it and actually I said factorization has been proven actually, starting from Sturman's work. So there are factorization theorems, right? So the fact that you can actually write this as so if you look at this, if you look at what it says over here, it says that there is this hard part and a soft part. And the hard part is actually, because hard meaning, there's a hard scattering, so large momentum transferred, so it is calculable within perturbative QCD. And the soft part is what you take from data, right? So this factorization, there is a factorization theorem and you can prove it. So it is different, it is much easier to prove, say, for EP processes than for PP processes, but it has been proven, at least to, the orders that they are computing, it has been established, certainly.
And therefore, it would be, shown at the level of about what, 5% or 1%?
No. Factorization is a theorem.
Yeah, that's a theorem.
Yeah.
But I'm saying from experiment, basically it looks like you're folding in some distribution that you get from lepton hadron scattering, proton scattering, let's say, and use it for PP. Is that?
Yes, yeah. So you have to redefine. So the quantity that you get for PP is slightly different at higher order from the quantity that you get in EP. So you have to do what is called a finite renormalization. So you subtract that portion, and then you get a universal distribution, and then you hide that extra portion in the cross-section itself. That is also part of factorization. So the factorization allows you to use the same Parton distribution functions in all these processes. And that also you can prove order by order.
Within a few %, is it?
Not within a few %, exactly. So the definition itself changes. So how you apply it is by changing the definition, so that the soft part that you pull out is always the same in all these processes. And the hard part anyway is calculable. And the difference between the soft parts of the two of them is actually a hard part which can be hidden into this hard part. That is the meaning of factorization. So what is actually uncertain is that, see, factorization tells you that there are all these Parton distribution functions. And we only look at the log Q squared part of it. Okay, but that is what is called the leading twist approximation. Now at low Q squared, there are what are called higher twists. Twist is this dimension minus spin of the operator. Okay, that goes like 1 by Q squared. So when Q squared is infinity, the 1 by Q squared parts just go to 0.
Yeah.
But at low Q squared, and especially for neutrino experiments, these higher twist terms are actually very large, and nobody really knows how to compute them. And HERA and such experiments don't have a large higher twist part because they're at high Q squared. So you have to go back to those old E772 and other data from old times to look at this higher twist part, and there are actually very large corrections there. So which LHC will not be subject to, but certainly the neutrinos cross sections will all suffer from these contributions. And really nobody knows how to compute them. So when they claim things like sterile and all, I am very skeptical. You can claim lots of things, but you don't know your distribution functions so well. Really, you don't know. Genuinely speaking, you don't know it very well.
With apologies to the experts, maybe I can just say, I don't know whether I'm correct or not, that the soft part refers to actually how from quarks and gluon level we are coming to the hadrons.
Correct. That is the Parton distributions.
Yeah. So
all the fragmentation functions,
that is independent of the experiment we do. In the experiment at the fundamental level, it is the quarks, gluons, etc. The partons.
It doesn't come out like that.
Finally, it's the long distance.
Yeah, it doesn't come out like that initially, but you can redefine it so that it is independent of the experiment that you do. Yeah. And a lot of the definition of the cross section goes into actually defining it correctly so that these are universal. In fact, that's also important to know. It will not automatically come out. You have to do a little work to make it come out. But that can be done. That is, I think, Vivek's question, that factorization can be shown. Not only can you factorize, but you can factorize with the same universal soft part. Yeah. In fact, it says here, right? Universal.
Yes, soft part, it says universal.
Universal, yeah. But they're arranged to be so. They don't come out automatically like that. They can be arranged to be so.
Okay. Are there any more questions to Indu? Okay. If not, once again, let us thank Indu. Firstly, I mean, I didn't mention in the beginning, but I must say that, this has been extremely on short notice. India's agreed to give this talk because the speaker who was scheduled had to withdraw at the last minute. And I also know that there were further difficulties, but in spite of that, she has come up and gave this talk. So thanks once again, Indu.
Yeah, thank you. Thank you.
It's
Always
nice,
a pleasure to
very
come
nice
and
talk.
talk.
Yeah.
Thank you, Satyam.
Thank you.
Thanks, everybody. Yeah.
Thank you.
Okay.
Just a comment to Indu.